Okay, so I guess the first thing we're going to address is going to be sensitivity. And when we're talking about sensitivity on the microphone, that can be a little complex because the problem is the first problem that I see with the microphone, no matter what microphone we're dealing with, is how clean the signal is. So that when you understand, I'm not going to write this out, but try to follow my arrow is that let's say this sound wave hits this diaphragm. Well, we haven't really got into all that yet, but just try to understand that what's happening with the diaphragm is attached to the front of the microphone, and then it's on this microphone, it's got a part of it that goes down here that has an inductor wrapped around it that has a magnet that it's wrapped around that the inductor material of the wire isn't touching it, so that it can go in and out, in and out, in and out as the waveform hits it. Now, we haven't really got into these microphones yet, so just try to follow along that. I haven't really addressed that whole issue yet, but that concept should be fairly easy to understand. So the sensitivity of this diaphragm, as it pushes in and comes back out, is going to do what? Well, if you take a line that's going like straight and you watch the arrow, as it pushes in, well, as the sound wave pushes it in, that it starts to go up in voltage. And then as it lets off, it's going to go down in voltage, right? So what's going to happen is as it goes in and down, another way to look at that a little quicker is it's going to go like jaggedy up and jaggedy down. So the wave's going to look kind of jaggedy going up and down because of the way the sound's hitting it, and impulse responses, early and late reflections, and all kinds of things. So it wouldn't be just a real steady climb. It would be kind of jaggedy looking, going up and down maybe and all over the place. And it would basically be like a pencil that's got from the side of it maybe, or the top of it, pushing on it to where it's writing it, as the pressure wave hits that diaphragm, it's causing the pencil to write this waveform, right? Now, we understand that from what I'm does that make sense? I hope I stated that in a way to where it made it sound very simple. Because the problem is after that very basic concept, what happens afterwards? The whole deal there is how clean is the signal. So that can depend on a lot of things. That can depend on the magnet, the conductor, any materials after that, in the signal flow path of the microphone. And some of those things might be real hard to address. And we're going to address some of them, but the initial part of it is going to be the diaphragm, and if we can find out how good these materials are, about how good clean of a signal that it's putting out. But first and foremost, we'll just talk about sensitivity. But we understand the concept that we're looking at just about any microphone. So, they're set up differently, but it's basically the same kind of concept. So with that in mind, you're looking at sensitivity. So the more sensitive the diaphragm is, the more accurate that's going to be. You may get a larger dynamic range between 0 and its highest level, and also all that waviness that's going on for like a complex waveform that you've watched those videos, that it's not always like a sine wave that's just smooth, that all that jaggedness is going to be a much closer representation of the actual audio signal. And so, that's a real simple concept. As long as it's not so sensitive to where it's just flopping all over the place, because then it's not just reacting to the sound wave. You might from it flopping around, like you hit a drum hit and it hits it, but it just keeps wavering and it starts drawing the line. Well, that's not accurate at all. It needs to just move and back and forth when actual sound wave hits it. So there might be a point to where it's too sensitive, to where it's causing floppiness. So that's something to take into consideration. So I hope I stated that very clearly, because what we're looking at with that concept is when we're looking at, okay, here we've got an impulse response, correct? And we've got the initial response, we've got the initial reverb, early reflections, and late reflections that are all going to be hitting that diaphragm, causing it to push in and bounce back out. That's going to be causing it basically with that apparatus to draw a waveform that's going to be output as the actual audio analogous signal, correct? I know that's a little complex, but basically that's what's happening. So, but the problem is they're not normally real steady. You look at some kind of impulse response in early late reflections, that it's not just some slope of evenness, right? I mean, they're dropping down. You're hitting, this one's hitting down there. This one's hitting way low. This one's hitting high. This one's hitting low again, high, a little bit less. You know, it's going to go like that depending on the acoustical environment. So it's really going to depend on how sensitive that diaphragm is from the sensitivity point of view. And we already talked about the quality of the components to give an accurate signal, you know, and so the first part would be that sensitivity. It being sensitive enough to capture that well and bounce back out where it's supposed to, and it not being so sensitive to where it flops around, so it gives an inaccurate reading, like, you know, it's registering, you know, impulse responses or reflections off of the acoustics of the room that didn't even happen. So I hope I stated that in a way that I was trying to do it, you know, without a bunch of math, so that it would be easy to understand without having to pull out a calculator and sit around and have you, you know, take some calculus. So hopefully that was stated fairly well. So let's take a little look at sensitivity and how they read it, or and how they, you know, make analysis of it. One thing really quick before we go on is just to make sure you understand, as the sound wave pushes in this diaphragm, it's increasing the voltage so that the voltage would go up. And as it comes back out, that it's decreasing the voltage and the line will go down. So that you can have a really good understanding when you're dealing with the acoustics, that this reverberation hit and is pushed harder on it as it's letting out before it hits this next reflection. That one's not pushing as hard, so that when you're looking at like this, it's not a sine wave, it's a little bit more of a complex waveform, that just like this doesn't look like a smooth line, that sinusoid won't be exactly smooth, because it's different levels of pressure pushing on it, so that sinusoid, you know, like if you're looking at this, that sinusoid coming out of there won't be nice and clean like that. It'll be a little bit rougher and more jagged looking. So I just wanted to address that again, because I thought I explained that pretty well, so that when it's like drawing it like that, with increased and decreased voltages from this going in and out, that, you know, it's basically drawing this waveform, you know, and it probably ain't going to look like that sinusoid nice and clean. Does that make sense? So I hope I made that real clear. And now we can go on and take a look about some of the measurements of sensitivity. Okay, so first of all, you have to figure out some way to measure the actual sound pressure, the SPL. So basically the standard is using 94 dB SPL, sound pressure level, to measure, and they'll call that 1 Pascal. So basically all that's saying is that, you know, is that 1 Pascal is the unit of measure that they're testing all of the sensitivity of those diaphragms, their sensitivity to the microphone, which basically works out, they're testing it with 94 dB, 94 decibels SPL, so that you have, you know, a standard that it's tested by. That's a very simple concept to understand. All right, the next concept to understand is when you're testing the sensitivity like we talked about, is that microphone is fed a signal of 94 dB. Okay, so what it's going to generate on this microphone is 1.85 millivolts. And we talked about as it increases pressure, it increases the voltage. So it's going to generate 1.85 millivolts, okay? So with that understanding, that if it's going to create 15 millivolts, that means it's more sensitive, correct? So, I mean, if the reading is higher, it's more sensitive, because it's pushing the diaphragm in farther, and it's giving it more millivolts. That's real simple to understand. So that you understand the increased amount of millivolts is basically an increase in sensitivity of the actual microphone. That's a real simple concept to understand. When you understand they're using a base structure of 94 dB, and then they're figuring out how sensitive by reading the amount of voltage that creates from the diaphragm being moved in and the voltage increasing. That's a very simple concept to understand. All right, so also they want it to read the sensitivity in decibels. So they've come up with a system that basically works with the other system of millivolts, and they call that dBV. So decibel volts. So what that's going to be with the standard of 94 dB, that when it pushes in and they test it with 94 dB, the reading on this one that we're talking about, it will be 1.85 millivolts or minus 54.5 dB volts. That's real simple to understand. So, and the lower this number is, the higher the sensitivity. So that's a real simple concept to understand. And if you look on this page here and this link, that basically you can see that they've actually have a calculator, and I'm sure that there's a lot of links on the front of this page or this YouTube channel for links to this also, so that you can, you know, have an understanding of what that's trying to tell you. So what would that mean? So when we're looking at the sensitivity, when we're looking at it, if we're going to get a reading that says minus 54.5 dB volts / Pascal. And we're also going to get in parentheses the millivolts, 1.85 millivolts. Now we understand exactly what they're talking about. And as long as we get this information that 1 Pascal is just a unit of measure of the SPL that they're using, that's 94. So we know what they were basing it on to get that information. So all that's real simple and to understand, correct? That's easy enough. The other thing to note, that it might have a frequency that it was tested at, like this one at 1 kilohertz. That's where it was tested at. Now that would be getting into frequency response. So basically that tells you that it might not be totally accurate, that sensitivity for the full spectrum, but at 1 kilohertz is where it was tested. And you'll have to look at the frequency response for more information about how all the frequencies are, you know, how the other different frequencies, it might be more or less sensitive. Does that make sense? And one thing we just talked about is the microphone sensitivity is going to vary with frequency. So basically they can test it at different frequencies with that system we're talking about, but basically you're probably better looking at the frequency response to get that analysis. The other thing we were talking about, how you get that reference of like minus 94 dBV, is because all the microphones will put out less than 1 volt. And so 1 volt would be 0 dB. So like when you're looking at the studio and it's like you're getting that reading that's minus 94 or something like that, it's basically that concept. Also, if you click on that link on the front of this channel, that those calculators, on this site, one of them is microphone sensitivity and conversion, that should give you any calculations necessary if you don't have one. Another site here is the National Institute of Standards and Technology, to get more information that might, for any of the technical equipment that you might have. Alright, so lastly, the generalized standard, that when we were talking about 94 dB SPOs, they're testing that at 1,000 hertz. I just want to reiterate that. And the last thing is, when we're talking about sensitivity, what are we trying to capture? That microphone is that the biggest concern you're going to have is not the initial response, is going to be how well it captures the environment, the acoustics of the instrument. Like if you've got a big tom or something, that the initial strike is going to capture that initial response, and even without a lot of acoustics or in a really acoustically well-treated room, that there might still be acoustics, you know, and late responses from that. So, you know, your sensitivity is going to increase as you're worried about that instrument and the aspects of its acoustical properties, you know, so that if it's either just an initial response and that's it, or if it's initial response and it has other responses afterwards because of its acoustical properties, and or if you're in an environment that you're truly trying to capture, that environment where you're really going to be worried about its early and late reflections and capturing all the nuances of that acoustically treated room. And if you keep that in mind as you start to look at them, that you should be okay with that understanding of what we talked about. And the next aspect would be to go compare some really good microphones and some middle of the road ones, and really understand what they're trying to capture with those. So I think we covered that pretty well, and I think we got a pretty good understanding, and with a little comparison we'll be okay. So let's go on to frequency responses.